Welcome to the massive open online course on Aspen Plus. In today's lecture, we are going to discuss about the hydrocyclone. The concept of hydrocyclone is similar to that of the cyclone separator. Only difference is that in cyclone separator, we had a feed that is a gas flow in which solid particles were suspended. But in case of hydrocyclone, it is a liquid feed in which the solid particles are suspended. That means in both the cases, solid particles are suspended in fluid medium, that is a feed. But in case of cyclone separator, the fluid is gas, and in hydrocyclone, the fluid is liquid. So that is the only difference. Otherwise, the operating principle, the construction, etc., everything are same. So just like a cyclone separator, a hydrocyclone also has a cylindrical top and a conical bottom. It also has a feed line that may be round shape, circular, or it may be rectangular shape. The fluid is inserted through this channel with a very high speed tangentially. And due to the geometry of the vessel, the fluid forces itself with an orbital path, just like it has been shown over here. And this orbital path has a downward axial direction. As it is with a high velocity and high speed and in an orbital path, a huge amount of centrifugal force is acted on that particular fluid. The purpose of the hydrocyclone is to separate the solid particles suspended in the liquid from the suspension. But the solid particles are in micron ranges. So gravity settling is not enough in terms of the residence time of the fluid inside the hydrocyclone. So purpose of creating the orbital path using a high-speed circular motion of the fluid, one can create a huge amount of centrifugal force that acts on the fluid and its particulate media. As a result, the heavier particles and the denser fluid move outwards to the wall of the vessel, whereas the finer particles and the lighter liquid media, they gather towards the axis of the vessel. So that way, the finer particles are separated from the heavier particles and lighter liquid is separated from the heavier liquid. And as the orbital path is having a downward motion, so the entire liquid media comes near the exit point and some part of the fluid comes out as underflow, and this underflow contains mainly the denser fluid along with the heavier particles. Whereas due to the mass balance and the force balance, the finer particles and the lighter liquid, their flow changes the direction. That means from the downward flow to upward flow. So an inner vortex is created over here that goes in an upper direction. And thereby it reaches somewhere here, and this is called the vortex finder. And the purpose of this vortex finder is to prevent the mixing of inlet fluid and the inner vortex. So the lighter liquid medium and the finer particles, they come out through this vortex finder as overflow. So that's how the underflow and overflow are separated. The underflow typically contains the denser liquid media and the heavier particles, whereas the overflow contains mainly the finer particles and the lighter liquid media. These are the typical operating ranges of a hydrocyclone. The suspended solid particles in the liquid media typically has a diameter between 5 and 200 microns. The diameter of the hydrocyclone itself, that is the cylindrical portion of the hydrocyclone, its diameter is typically between 1 centimeter to 60 centimeter. The pressure drop across the hydrocyclone may be anywhere between 35 to 345 kilopascal, and the separation efficiency that can be achieved through hydrocyclone, it may be anywhere between 2% to 98%. And the solid concentration of the feed material that we can use in the hydrocyclone, that should have less than 11% volume fraction or less than 25% of the weight fraction. That should be solid concentration in it. Now let us get introduced to various dimensions of hydrocyclone. First, the inlet geometry, that is the inlet pipe of the hydrocyclone. So, as I said, this can be a round-shaped pipe or a rectangular pipe. So, if it is a round-shaped pipe, then you have to specify the diameter of the round inlet, or if it is a rectangular shaped pipe, you have to specify the inlet width and inlet height. And there are three height components in the hydrocyclone dimension: height of vortex finder, height of cylinder, and total height. Now, height of cylinder is straightforward. It is the length of the cylindrical portion, and total height is the summation of the cylindrical height as well as the conical portion height. And this is the height of vortex finder. This pipe is called vortex finder because the tip of the pipe should reach the inner vortex of the conical portion, so that the lighter liquid medium and finer particles trapped in the vortex can be accessed by the tip of the vortex finder so that they can get released as an overflow. And these are the diameters and cone angles of the hydrocyclone. This is the diameter of the cylindrical portion, DC, and DV is the diameter of the vortex finder, and DA, that is the apex nozzle diameter. This diameter is useful for calculating the underflow. Alpha is the cone angle and theta is the full cone angle. So theta will be equal to 2 alpha. R main is the radius of the cylindrical portion of the hydrocyclone. So it is basically the half of the diameter, EC. Similarly, the R vortex is the radius of the vortex finder. Obviously, this is half of the diameter of the vortex finder. Now let us go to the Aspen Plus simulation window and look into the hydrocyclone block and see what are the parameters that we need to fix. So this is the simulation window. You will find the hydrocyclone in the solid separator over here. So let us bring it over here and connect the material streams. So this is the feed, this is the liquid, and this is solid. Although they are called solid and liquid, but this stream will mainly have, or is expected to mostly have, solid, but it will also have some liquid component or the heavier or denser liquid component. Whereas, although this is called liquid, but it also will contain some finer particles that will go through the inner vortex that we have discussed just now. So let us rename them. Feed. This is liquid and this is solid. Now let us go to the block B1 and C input. Okay. So here you will find two types of models for calculation. One is solid separator. As you have seen for other cases of these solid separators like cyclone, V-scrub, centrifuge, filter, C filter, the solid separator options are all same, so nothing new to learn over here. We will directly go to the hydrocyclone model and let us see what are the things that we have to fix. Again, hydrocyclone can be run in two modes. One is simulation, another is design. In simulation mode, or it is called rating mode, the hydrocyclone calculates the particle diameter with 50% of separation efficiency from the user specified cyclone diameter or hydrocyclone diameter. Whereas in the design mode, or it is also called sizing, hydrocyclone determines the hydrocyclone diameter required to achieve the user specified separation efficiency. So in one case, we have to provide the hydrocyclone diameter and that will calculate the particle diameter with 50% separation efficiency. And in the other case, we will specify the separation efficiency and hydrocyclone will determine what will be the hydrocyclone diameter that will be required to achieve that particular separation efficiency. So here you see, when you have simulation mode, then you have to provide the diameter and the number of hydrocyclones. But the moment you choose design mode, then you have to give the maximum diameter for a particular hydrocyclone efficiency that you want to achieve. Then comes the efficiency correlation. We have several options like Bradley, Pleat, Nageshwar Rao, Modified Brown, and user specified. And type of calculation, that is Ritema rectangular, Ritema round, Bradley rectangular, Bradley round, user specified, and user specified ratio. This rectangular and round, these are the types of inlet that we have to specify. If we use a round shaped inlet, then we have to choose the Ritema round or Bradley round. And if we use the rectangular shape inlet, then we have to choose Ritema rectangular or Bradley rectangular. Or we can give the user specified or user specified ratios for the dimension. We will discuss it one by one. So first let us understand what are these efficiency correlations. Now the separation efficiency in hydrocyclone is given by this particular equation. It says efficiency E is equal to mass under flow rate of the solid by mass feed flow rate of the solid. That means, suppose this is the hydrocyclone. So this is the feed and this is the underflow, this is overflow. So Fs is the mass flow rate of solid in the feed and Us is the component of U, that is the mass flow rate of solid in the underflow. then US by Fs, that is the efficiency. In other words, we are not talking about the entire flow rate. That means we are not talking about the mass of the liquid portion that is coming along with the feed. We are taking only the mass of the solid in the feed. So what is the fraction of that is going out through the underflow. So that is the efficiency. In order to achieve 100% efficiency, we should have the entire mass of solid to go through the underflow. But as you can understand, that will never happen because there will be some finer particles which will come to the inner vortex and it will move towards the vortex finder through an upwardly flow and it will exit through the overflow. So that component will go away. So it will always be less than 100%. But we have to maximize the efficiency. That is the requirement from the user's perspective. You can take this as an example of a typical efficiency curve for hydrocyclone. You can see that any particle above 3 micron is expected to go through the underflow. In other words, the particle size above 3 micron are considered to be heavy particles and they are expected to go to the underflow, whereas the particles less than 3 microns, they are regarded as finer particles. So they are expected to go towards the axis of the inner vortex and they are supposed to go in an upward direction and eventually go out through the vortex finder. So if you talk about the particle size, say 1.5 micron, then say 45% of particles having size 1.5 micron is expected to go through the underflow and 55% of the same particle size should go through the overflow. Here you will find one interesting thing. This curve does not go to 0. It will reach somewhere above 0. In this case, it is 25%. That means no matter how small the particle is, there will be some particle which will go through the underflow. That is because the entire fluid media is highly turbulent. And in this highly turbulent media, the finer particles are expected to be uniformly mixed within the fluid media. So when the heavier particles and denser fluid media are going out of the hydrocyclone through underflow, then some amount of the finer particles are also expected to go through the underflow. In this case, 25%. So this is the typical user-defined efficiency curve that you can use in Aspen Plus simulation window. Now, if you do not want to use the user-specified, you have the options to use the Bradley correlation, Pleat correlation, Nagesha-Rao correlation and modified Brown correlation. So we shall go and find them one by one. But there is also a concept of corrected efficiency, which is a ratio between E minus RF by 1 minus RF, where RF is the volumetric ratio of underflow to feed flow. And this information is there in material split. So if you go to material split, you will find this RF, and this RF, that is underflow rate by feed rate, is obtained by this equation where S is equal to volume split, that is underflow rate by overflow rate. Now, how you can calculate this underflow rate by overflow rate? For Bradley, Pleat, Nagesha-Rao and Brown, they are given. S is equal to beta into dA by dV to the power 4.4 into V to the power minus 0.44. Beta is a constant, dA and dV already you have learnt in the hydrocyclone dimension, and V is the inlet volumetric flow rate in gallons per minute. So through this, S can be calculated, and from that RF will be calculated. Then if you use split, then you have to provide this information. Obviously, the density of the suspension will be calculated by Aspen itself from its property database, and all other information like this dV, dA, dC, F4. F4 is the adjustable parameter that you will see when we see the pleat separation efficiency. CV in, pressure drop. Those are the things that we have to specify. And then Nagesha-Rao model, it is a bit complicated because you have to provide all these things, KW1, lambda, theta, and RF can be calculated directly without calculating S. And here also you have to provide all this information. K is the adjustable parameter, theta is the full cone angle, density of the suspension, and all other dimensions that we have already learned about a hydrocyclone. Similarly, Brown model is far more complicated. You can just read through them, or you can go to these particular hydrocyclone references to learn further. So that is about the material split to find out the RF. Once you know the RF, you can get the corrected efficiency. Then come back to the efficiency using Bradley. Now, if you do not want to use the user-specified efficiency the way it has been given over here, if you do not want to use this, you have to use either Bradley or Pleat or Nagesha-Rao or Brown. So for that, use Bradley correlation where E dash is equal to 100 into 1 minus exponential by d d50. So this particular equation where d is the diameter of the solid particles to be separated, and d50 is the particle diameter for which 50% of feed passes through the underflow. So this d50 will be calculated by this particular equation. It will be done by Aspen itself. You just have to provide this information. Okay, V in, DC, D, all this information that you have to provide. Here alpha is the inlet velocity loss coefficient. Do not confuse it with the cone angle. Okay, theta is the cone angle. Density and viscosity of the liquid will be calculated or will be taken by Aspen Plus from its property database. So you do not have to bother about them. So that is how Bradley separation efficiency will be calculated. Suppose you choose split, then you have to provide this information. Parameter F1, parameter F2, parameter F3, parameter F4. Then the pleat corrected separation efficiency will calculated for each particle size class, that is diameter d, as this one. So E dash of d is given by this equation where m is calculated from this particular equation. So these are the parameters. So this is F2, this is F1, and F4. You remember we have seen F4 over here. So these are the adjustable parameter for pleat. Okay, so F1, F2, F3, F4 that you have to provide over here. So the detailed calculation are given over here. So interested readers can go through in detail. And here another factor is there. It is said the separation efficiency calculated by this model may be adjusted by fish hook model. Now let us understand what a fish hook model is. For that you have to go to the fish hook effect. Now I already explained why the separation efficiency cannot go beyond a certain point. A few minutes back only we have discussed that the finer particles are evenly distributed in the fluid medium. So when the fluid comes from even the denser media and goes out through the underflow, then the finer particles are also escaped through the underflow. So there should be a non-zero minimum for that value. So it is always expected to go to a non-zero medium. Okay. So the separation efficiency curve therefore has its minimum point at the volumetric flow split. So this point is called the volumetric flow split. But then it is often observed that the finest particles, the efficiency even increases again. So it increases again like this. So this is called the fish hook effect. Because this separation efficiency curve looks like a fish hook. So that is called fish hook effect. And this fish hook model has been given by Roldan and Vilasana. And this is the model. So in this model, you will find Ka and Kb. So these two parameters have to be specified. So fish hook model, coefficient Ka and Kb have to be specified. So this is about Pleat model. Then Nageshwar Rao model. Here you have to provide the efficiency parameter alpha, beta, Kd0, Kd1, Kq0, Kq1, Kw1, Kv1 and exponent and density correction. So alpha, beta, Kd0, Kd1, all of them can be explained over here. For that you go to the separation efficiency again and you see the Nageshwar Rao model. So here you will see you have alpha, beta, Kd1, Kd0. So all those factors are there. And it also has a fish hook effect, the parameter beta. So beta is set to 0 if no fish hook effect is considered. And if there is no fish hook effect is there, then beta star has to be taken as 1. And if there is some beta value chosen, then beta star has to be calculated such that the predicted corrected cut size D50C is preserved. So you just go to the fluid recovery and you can see for the Nageshwar Rao, here you have to provide this KW1. Okay. So all those things you have to provide as per the requirement. Similarly, you have modified Brown. You can go through the modified Brown references in detail. There are several options. You can go one by one. Lot of flow speed models are there. Okay, so these are about the efficiency correlation. And these are the type. Now, if you choose user specified, then dimensions will be activated. So just go to dimension. it will ask inlet configuration. Inlet configuration can be rectangular or it can be round. If you choose rectangular inlet configuration, it will ask for height of inlet and width of inlet. If you choose round, then height and width will be deactivated and diameter of inlet will be activated. And all other things will remain same. That means you have to provide the length of the cylinder, length of the vortex finder, diameter of the overflow, diameter of the underflow, and cone angle. So all of them you have to provide. So diameter of the hydrocyclone already you have provided, and you have to provide other dimensions over here. So this is about user specified, but if you choose user specified ratio, then the dimension will be deactivated, ratio will be activated. And again over here they will ask you the inlet configuration, either round or rectangular. As it is round, diameter of inlet has been chosen like this. If you choose rectangular, then this will be deactivated, height and width will be activated. But here you have to provide the ratio. That means ratios of cyclone diameter. That means length of cylinder by diameter of the hydrocyclone. Length of vortex finder by the cyclone diameter. Similarly, all of them you have to specify as the ratio to the cyclone diameter. So either you have to give ratio or the dimension. So either way you have to specify. So this is about the user specified ratio or user specified dimension. But you can choose Ritema rectangular also, or you can use Ritema round, or use Bradley rectangular, or use Bradley round. For that, there are references available. So you will find the dimensions over here, Ritema and Bradley. So D in, H inlet, W inlet, DV, DA, all of them are fixed. So if you use this kind of type, then all these dimensions are fixed by Aspen Plus itself. You do not have to give separately. Then these are the pressure drop calculation in hydrocyclone. For Bradley efficiency curve, the pressure drop will be calculated in this fashion. For pleat efficiency curve, you will see the adjustable parameter F3. So you had F1, F2 and F4. F3 was missing. So for pressure drop calculation, F3 will be useful. Okay? And various dimensions are used for this calculation of delta P. Nageshwar Rao also, you have to use KQ0 and KQ1, then Brown. So these are the references that you can go through. Now let us solve an example problem and learn it better.